Okay. Yeah, I guess we're live now. All right, cool. Well, good morning, everyone. Or me, whoever's supposed to watch this a long time from now. This is. I'm hoping the audio's okay. I have no way of knowing. I guess I can watch it myself. Let me hang on. This is. Yes. Okay. Audio's fine, and this famous static is still here. I don't know how to get rid of that. Don't ask. So so basically what we're just going to continue. So what we're doing is this right here. We are doing this problem still. This is a CFD problem. It is essentially a computer chip being cooled with a water cooling plate, and the water cooling plate cannot get above 40 degrees Celsius in any location, and because of that we have to change material properties so that we can have an increase in heat flux, because normally you want to push the limits as to what power output you can put inside of a computer chip. So we're going to look for some materials that have a higher conductivity coefficient of 160, which shouldn't be too bad. Copper is good, and some other materials. Now we want to keep in mind some other material properties like workability, toughness, maybe some, I don't know, corrosion resistance. Pure copper is probably not a good idea. You probably want some coated copper, or some kind of, and something with a little zinc in it, because you can't have, or something, because you can't have it be too excuse me, you can't have it be too corrosed, if that's a word, because of the water flowing through it, and the water is going to be some kind of ionic. And some electrolysis happens, and boom, you got rust, and you can't have that long term. This is not going to last. So I'm going to take a sip of coffee. I have here black coffee. This is black coffee over ice. No sugar, no milk, no cream. Very nice. If anyone doesn't get that reference, go learn how to work Arduinos with Paul McWhorter. You can use this kit, which is a Sunfounder Elite Explorer mix, but that's pretty expensive. It'll run you about $100. But if you don't like that, you can get this guy, which he has another equally good series on. And this is the Elegoo Super Starter Kit. It comes with all kinds of stuff, and it's $30. It comes with a servo, it comes with all kinds of wires, it comes with the breadboard, it comes with the actual control board itself, it comes with an extension, it comes with a motor driver, it comes with a servo motor, a DC motor, and a stepper motor. It comes with an ultrasonic sensor, a motor relay, a 7-segment 4-digit display, a 7-segment 1-digit display. It comes with an IR sensor, a remote, and a fan blade. And there's some other stuff. There's like an op amp in here. There's the motor driver itself. There's a potentiometer, which if you don't know what that is, it's a little knob that you can turn and adjust resistance, so you can control things. You get a little, oh, this one's cool. You get a joystick. Look at that. Look at that little joystick. It feels so good to mess with. Man, this is so fun. And you get a AA battery with some other stuff. You get photo sensors, 4 buttons, a transistor, a thermistor, and oh, can't forget about this, and an LCD display. $35. Quite nice. Yeah, I'm very happy with this kit. Not to mention the control board itself. Now, I will go ahead and advertise myself for a little bit. Excuse me, I have to find it because I don't know what. Oh yeah. So soon, if you buy the Elegoo kit, I have modeled and I am 3D printing these beautiful cases. Look at this guy. You get a nice UNO R3 and a nice Arduino logo, right? All right, and you can. There's a little guy there. That's how that looks. And you can see in here that you can actually see the pins. You can see the pin numbers. You can see all the lights. Just comes off like that. The control board sits in there. Look how beautiful that guy is. It'll focus. Yeah, let me just focus on my face. Yeah, see how beautiful that is? It has 3 little thingies in there to help it stabilize. So when I slip it on in here and I close it shut, it stays put and it doesn't rattle. So if you want one, tell me to sell them, because I probably haven't made an Etsy account yet, and I should, because I don't know, what do you think, like $15 a piece, I guess, because of shipping and stuff. I don't know. I have to package these, right? All right, so man, coffee's good. All right, let's see here. So where we left off, essentially, we have this color map. This color map is, each color is a unique style of equation that varies in shape to a degree that I would want to rewrite it from scratch. I usually don't rewrite them completely from scratch, but it's pretty close. Like, you have to rework it so much. So this is better than writing equation 1 and just write it out. Equation 2, write it out. Equation 3, write it out. And then that takes forever. There's just no reason to do that. We have the power of copy paste. So we have finished the dark blue. We have finished the light green. We have finished the yellow. We have finished the purple. We have finished nothing else. We have yet 3 more colors, which is halfway. We have these red pieces, the light blue pieces, and the orange pieces. I guess we're more than halfway. There's 7 colors here. Okay, so in order to do this, I'm going to pull up where we're document. This is my other report. I'm copying it in here so that I don't have to rewrite a template. I don't have a proper template. So this is our actual, where we left off. So these are the equations we have so far. So we have node 1, node 5, 24, 28, node 2, 3, 4, 10, 13, 18, 23, 19, 11, 15, and 7, and 9, 12, 17, 20, 21, 22. Okay. So keep in mind, we're going to solve all of these equations for their respective temperatures. And what we're going to do is something like this, where we have this matrix here, and I'll say, and it'll be a 28, so this is an 8 by 8 matrix, because we had 8 unknowns and 8 equations. And essentially what I would have is I would get, like for equation 1, for example. Let's look at the figure here, because this will help. Hang on, excuse me. Gotta find it. Okay. So let's look at this, for example. So equation 1, what does that depend on? Well, it depends on T2. There's a ghost T2 over here, remember, but it depends on temperature at point 2 and the temperature at point 6. Okay. So on equation number for node 1, on equation 1, we're going to have temperature 2 and temperature 6 in that equation. So when we have here, we're going to have for the row 1, which is for our first equation, rows are equation numbers, columns are temperatures. So for row 1, element 1 is going to be blank, because we don't have a first temperature in there. We're not dependent on the first temperature, right? Okay. Oh no, we are, because Fourier's law says Ka T minus T, delta T. Delta T is the difference in temperature between one temperature and another temperature. So that means you have Ka T2 minus T1 and then Ka T6 minus T1. So you got 3 temperatures in that equation, T1, T2, and T6. So your first element would not be blank, your second element would not be blank, and your 6th element would not be blank. They would have coefficients. Your diagonal matrix here is your coefficient matrix. Your temperatures here are going to be your solution vector. These are what you're solving for. These are what you want. These are your constants. A lot of these constants are going to be 0 in our case. They weren't constant here because this was a transient problem. And so we solve this, in this case, we solve for the previous time step, and then we use those answers as initial conditions for the next time step, and then once we got the new temperatures, we set those equal to our now present time step, and then we set them equal to the past time step, and then now we update the past time step with those new temperatures, and then we repeat the process again, and we just keep doing this until we get all the time steps for every single node. And so basically you'd be able to draw a graph for example, T1. You'd be able to say, T1 changes over time like this, T2 changes over time like this. So you get how many 2D plots? You get 8 two-dimensional plots showing the change in temperature over time. And that's basically it. It's not rocket science, right? It's on my right, it's on my right. I know my left and my right. Okay. I gotta stop stalling here, because this is, man. Alright. The nodal equations. So, the nodal equations for nodes. Now, I need to figure out what nodes these are. So I have this guy here. I'm gonna pull up YouTube Analytics because I'm very tempted to. I have 2 monitors here. I'm very tempted to use the other one and not show y'all what I'm doing. So I have to put this up so I can actually interact, and my girlfriend might hop on here and send me a little comment. Assuming she's not too busy. I might text her. So, right now, I have this PowerPoint document saved to the PC, and it corresponds with this. So, I want to do the hard ones right now. Do I? Yeah, I can do the hard ones right now. No, I kind of want to save the hard ones for later, for the last. Let's do 25, 26, and 27. Those are easy. Let's do those. Those are simple. Okay? Those are really easy. Alright? So this is going to be node, and I can do things like this, right? You know, I really don't need, I can just do this and open this. That's not what I want. Hang on, let me get my screen. Let's see, CFD. Temperature distance. It should be in my folder. Where I just took the screenshot. Where's my? Oh, this isn't the screenshot. Okay. Hang on. Oh, so much thermo stuff lately. Yes, you. Okay. Do that. Yes. Yes. Yep. Okay. Oh. Didn't know that could happen. Alright. Can I scale you accordingly? Because both of y'all are more vertical images. So can I do this? Oh, that's kind of nice. Alright. Yeah, we like that. Okay. So now we have our setup here. We're doing equation for nodes. An equation for nodes 6 and 14. For nodes 6 and 14 are very similar, whereas this one's the equation for node 6 is written. The equation for the other respective node is bound easily. Okay. She texted me. Okay. Is. Alright. Cool. let's take this big guy and then just copy paste, so I don't have to write something completely from scratch. Okay, we are doing node 6, so I'm just gonna, okay. Okay, so I'm really happy I don't have to deal with PowerPoint anymore, because what I was talking about beforehand was PowerPoint is about the most unintuitive way to draw. I do not know how anything gets made in PowerPoint. I just don't. Like, you should be able to switch to metric. You should be able to say, draw a line from here to here and make it this distance without having to do Pythagorean theorem. And even if you did have to do Pythagorean theorem, fine. Let freaking PowerPoint do it. Why is a line drawn with the diagonal of an imaginary rectangle? That's terrible. Anyway. Alright, I'm gonna just keep going here. Okay. So, at node 6, we go top, right, bottom, left. That's the order. From the top, I have conduction from node 1. It travels delta y. It hits delta x over 2. It's never done that before. That's what I've been wanting it to do. If I highlight something and then I click fraction, it should make a fraction with that as the numerator. It should always do that. I can't believe it actually just did that. That is nice. Okay. Just to clarify, it comes from 1, it hits 6 at delta x over 2. Conduction from node 1 hits 6 at delta x over 2. Isn't it surprising I don't have to mention the coming from area like in do it radiation? Heat transfer due to radiation is actually quite difficult. I'll specify that now, although I haven't done radiation in a long time. This is the Arduino that you get in the Sunfounder kit, and it is pretty sweet. As you can see, it has this LED light board right here that you can make cool little patterns with, and yeah, and it has its own little case that comes in the box with it that you can actually screw it to, and it's nice. I'll probably make something for this too. But this gets powered with USB-C, nice reset button, no other switches, and it has a little plug in the back there, right there. You can see it there. That is a motor driver little thing guy, I think. Anyway, if not, then I probably look dumb. Anyway, so let's say this thing is being irradiated on by this thing. This thing has an area, this thing has an area, but this thing doesn't see this full frontal area, because if it did, it'd be like that, but it's not, it's like that. And this might not be full frontal to this either, it might be like that. So both of these things are off, and this thing's radiating to this thing, and there's a square cube law, or the where you're reducing intensity with the square of distance because you're going out, right? So there is a way to find this value called the spectral intensity. Oh, and also you have different wavelengths of light that correspond to different types of radiation. So, because you have gamma rays, you have radio rays, whatever, that's all light. It's just different intensities, and they all have different energy values. So the idea is, what is the spectral intensity of this radiation? So first we need to talk about something called a solid angle. What's a solid angle? Solid angle is a 3D angle. Think about it like a cone. It's a cone. That's all it is. That's all a 3D angle is. It's just a cone. So, a solid angles are made, so real angles are measured in radians, Solid angles are measured in stradians, and these are completely different. I don't think there's a conversion factor from square radians to stradians. It's not like areas. So essentially, spectral intensity is, I believe, watts per stradian per nanometer squared. So stradian is the stradian. So spectral intensity is weird. I believe it is the stradian, watts per stradian per nanometer per lambda, which lambda is the frequency, and nanometers is the hang on, I gotta look it up. I don't remember. Definition for spectral intensity is awesome. Find it. Hang on. It's insane. Yeah. So, nanometers is the wavelength. Nanometers is the wavelength. Lambda is the frequency. You can have those contradict though, because if you have a high wavelength and a low frequency, then you change the speed of light, right? If you have a high wavelength and a high frequency, you change the speed of light. You've increased it. So that doesn't make sense. It must be what this is saying, that you have per unit frequency or per unit lambda. You have two different things, because you can go from frequency to wavelength and back and forth because light's constant. So, no matter what energy it is. You know, radio waves, they have a wavelength of like kilometers. Microwaves have a wavelength of like centimeters. So what you can do is put a rack of cheese in the microwave and not rotate it, and you'll see that some of it is cooked and some of it's not cooked. Where it's not cooked is when the wave is doing this and it's at a focal point, and there's no amplitude change there. When you get the cheese cooked a lot, it's because the light's doing this. So cool. Anyway, the per unit wavelength. The SI unit for the watt per unit stradian meter is watts per stradian per meter. Which is also not what I remember it being. I remember it having meters and nanometers in the same equation, in the same unit, and I thought that was insane. Because normally you would just say, oh, meters and nanometers, those cancel out or something. No. Because they're meters and nanometers of different things. The meters is how far away they are, right? How far away they are. And the stradian and the nanometers is the wavelength of the light. So it gets really, really insane. But, yeah. I'm going to stop stalling. I really do need to work on this. Okay. Let me go to the bathroom real quick, and then I'm going to get started on node 6. The first part is done. We need to do conduction from bright next. Okay. we're back. And okay. All right. So okay. Let's lock back in. So node 6, the right side, we have conduction from node 7. Do we have anything else? No. Nothing else. Nothing else. Just conduction from node 7. It's traveling delta x, but it only hits delta y over 2. Let me see if I can do the same thing I did before. But it only hits delta y over 2. Okay. Delta x, or sorry, the bottom, what it's hitting from the bottom, we have convection. So h times, what's our area that it's hitting? What's it hitting? It's hitting the convection is hitting it's hitting delta x over 2, I guess. Delta x over 2L. What are the two temperatures? They are they are T infinity minus T whatever, okay. They are T infinity . You might wonder why I'm doing T infinity minus T whatever instead of TS minus T infinity. The reason is I'm talking about the heat transfer going into my control volume, not the heat transfer leaving. TS minus T infinity is leaving. T infinity minus TS is coming in. Okay. T infinity minus T6. X over 2. Yes. Alright, this is where I'm thinking that there might be a problem here. And it would only be at node 6, because that's that. No, it could be at node the node 5, 28, 23, through 10 as well. There's symmetry there. So when it hits the bottom, is it hitting at that full? Is it hitting the full distance, or is it not? I would personally argue that it is. So conduction from 1 to 6, it would actually be hitting all of delta x. I've got to ask. T1 minus T6 divided by dy. Is that area A equal to dx L dx or A equals L dx over 2. Divided by d, no, it travels dx. Hits dy. No, I'm getting a mask. I'm getting a text message that I can like just ask everyone. There should be a select all feature. Copy. Yeah, so I'm thinking that node 1 to node 6, the area that it would be hitting would be the full delta x, because it's a symmetry. And that would also apply to all the corners, and it would also apply to, yeah, so that's kind of the conundrum here. Alright, keep that in mind, I guess, as I go along, but I'm going to keep doing it with the mirror technique and not doing that. So for right now, delta x over 2 is what number 1 hits to 6. Okay, and I can go back and change all this eventually, but I do not want to change it after writing after trying to simplify, because that would suck to not get right answers. It'd suck. Alright. K dy. Okay, so alright, so conduction from the left on node 6. What do we have? We have K. Conduction from node 7 into node 6. It travels dx and it hits dy over 2. Alright, so there's that. The equation for node 6 is thus. The equation for node 6 why am I italicized? That's not good. Alright, whatever. The equation for node 6 is this. Take this guy like that. What? Are you serious? I don't get it. Okay, whatever. Yep. Equation for node 14 is this. Okay, so on 14, on the top, I've got convection. So I'm going to now take this convection term and put it here instead. We have convection from the fluid into that control volume, which would be a distance of x over 2, t infinity minus t 14. Alright? From the right, you'd have it hitting delta y over 2, and you'd have 15 t 15 minus t 14. On node 6, on this part, on the bottom, you'd have conduction from node 19, into node 14, alright? And it travels delta y, and it hits delta x on 2. So let me just check this again. From the right, it hits delta y on 2, and it tells us that for this, it travels delta y, and it hits delta x on 2. Okay. For this, for the left, we have a, this is a T7 prime. We have a ghost 15 hitting a 14. It's traveling delta x and it's hitting delta y on 2. Alright, equals 0. Cool. Alright. So that is the two light blue sections. Let's do the orange. So 25, 26, and 27. Let me make sure I don't have those already. believe I do. Yeah. You'll have nodes for 25, 26, or 27. 14 is this? Alright, let's do the nodal, the nodal equations for the nodal equations for 25, 26, and 27 are all very similar. This one's this. 25 is right there easily. Alright. So, let's find those. Okay. How we do this? Take this guy, just copy this down here. The nodal equation for node. The equation for node 25 is thus. Alright. There we go. For 25, I've got from the top conduction. I've got from the top I've got conduction from node 20, so let's do 20 here, to 25. It's traveling delta y and it hits all of delta x. So I'm going to copy this top part, Control C. Alright. From 20 to 25 it hits all of delta x and it travels delta y. From the right, I have conduction from node 26 into node 25. I have it traveling delta x and it hitting delta, and it hitting all of just delta y on 2. Okay. From the bottom, this is the weird one. Alright, from the bottom, I have my flux multiplied by an area that flux hits, and the area that the flux hits is going to be all of my delta x L. From the left, I've got delta y on 2 times L. Yeah, because it hits that. It's going to be 24 to 25. And it travels all of delta x, and that equals 0. Okay. 26. There's 21. No. Yeah. So 21 conducts to 26 from the top. 27, 26, and then delta XL 25, 26. Then I do the same thing again. Nope. I just add 1 to all these numbers. Okay, that is orange done, and now I have the 2 red sections left. Hang on, I'm getting a message here. The area for node 6 is both both top and side directions. I don't think that that's right. Hang on. New slide. We're making a schematic, people. Here's my little node 6. He's very happy. Alright. On my node 6, I'd like to insert a line because I can't draw a line. My node 6's control volume is going to look like I guess I'll draw a box. And it'll have no fill. No fill. Alright. And so that's node 6. So here's node 1. Why is it so big? Alright. This is going to be delta y. realized I was still in the 5 section. I hope I haven't done something weird. I don't think I have though. I don't think he's right. It's both delta x. How I can see. Okay. So, as weird as it is, we are not considering, we're just going to continue as we have been. We're doing the control volume as we see it and adding a reflection. That's it. 25 prime is the same as 25 all stuff. It just doubles it. So, anyway, this is very strange because that should not be the case. Anyway, well, that's nice. That means I don't have to go fix anything and we can just start solving equations. I'm going to take another sip of coffee. Salute to Patrick Star. All right. So, man, I love Cal Harper so much. Such a cool freaking dude. Thank you, God, for him. 25, 26, and 27. So, alright, node 8 in the null equation, the null equations for nodes 8 and 16 are very similar. Very similar. Thus, once equation for node 8 is written, the equations for the other respective node is found easily. The nodal equations are very similar once the nodes are found easily. Alright, good. So now what we do, I'm probably going to write this one from scratch. I'm probably just going to write this straight from scratch. So, node 8. We're looking at node 8 now. Conduction, okay. The area that node 8 experiences from node 3, right, is I just realized I'll just never see any of the people that I worked with again. Like, I'll never see Cal again. I'll probably never see him again in my life. No, I'll see him at graduation. No, I'll see him again. No, I'll see him again. Just writing all the math out, it's all the math that's been on that whiteboard. It's hard to believe. It really is. I'm not a math guy. But I can get around. I can get by. But if you give me some weird stuff, anything with logarithm, change of base, anything Lagrange, anything 3D cal, that's tough. Or you give me any eigenvector or weird terminology, that stuff. I don't know that stuff anymore. But the linear algebra course, you do remember kind of some of that stuff. And if you, the goal for school is not to necessarily learn it all such that you can retain it all at once. No one retains it all at once. No one does that. None. No, absolutely not. You forget a year. Like if I was to take my, I had dynamics controls last semester. If I were to take that final exam right now, I would fail it. I'd get like a 0. Like seriously, I'd get a 0. But if I was working as a controls engineer and a guy was like, "Hey, we're gonna do Ziegler-Nichols tuning on this thing. You know what that is?" Be like, "Oh yeah, I kind of have an idea of what that is," and that's so much better than having no idea what that is. I kind of know what it is, that you kind of tune your P, I, and D terms based on the frequency of the oscillations of your system when you're running it. Like, I kind of know what that is. And so he can refresh me on some of the details, but he doesn't have to teach me from scratch. And that is so much better. It's just like these equations here. I can take this equation right now, and I can copy it, and I can put it here, and then adjust it to make a new node. Even if that node is way off, because I have most of the elements there already, I can just move them around. But and then I can check it. But to write the whole thing from scratch, yeah, you build this foundation, but it's so much harder to do. And if you had to do that over and over and over and over and over again, you can't do it. That's why linear algebra, like, you have to take the full crap courses. You have to do that. You have to take history. You have to do all that. And history you have to take repeatedly because people forget. And then there's indoctrination also. Every state has their own idea of what they want their kids to learn and know about other countries. We really are like Europe in a way. Except, because we have a lot of land, but we have a supreme leader called president. And there is a European Union now. But I don't know if there's a leader of that. I don't know exactly how all of it works. I just know the people, some of them, and what they've done. It's good to know who to listen to and who not to listen to. Because some people are credible for a time and then they're suddenly not. That doesn't mean they were never credible. And that doesn't mean they couldn't ever be credible again. People change all the time. Every day someone is new. They just have memories that they fall back on. For node 8, we're going to take it one side at a time. And it's going to be real simple. Node 8. On the top, it's just like node 9, right? I have conduction from the top. Well, what does that conduction look like? It looks like, well, from node 3, what can I see of node 8? If I'm looking from node 3, I can see all of that delta x. I can see all of it. I can see all of that delta XL. I can see all of that stuff. Alright? And then, if I was to, for example, those are really small. Is it supposed to be like that? That is not. Okay. We are gonna take a template. This is a formatting template. So in that case, I couldn't even teach it. I had to just, and it only took me a couple seconds to be like, all right, I'm just not doing this. I'm getting somebody else. From node 3 to node 8, what can I see? I can see all of that sweet, sweet delta x. How far do I have to go to get to node 8? I have to go all my delta y. Alright. From the right, well, how much can node 9 see of node 8? Node 9 can see all delta y of node 8, so we're going to copy this and paste it. It travels all of delta x, node 9 to node 8. Alright. Now, from the bottom, this is where it gets fun. Okay. I'm going to go ahead and get rid of everything else, and I'm going to put a big old bracket here. That matters. I'm going to put a K here. And then I'm going to put a bracket here for the A. And then I'm going to go outside that bracket and I'm going to put my fraction. And then I'm going to add another one of these. Okay. And then we'll close it with a plus. And then we'll have some stuff that comes from the left, which will be somewhat the same format. Of course it does that. Now, hey, what if I make it smaller? Okay. Alright. Let's see here. From the top, I have conduction from node 3 to 8. It hits all delta x, it travels delta y. I have conduction from node 9 to node 8. It travels all of delta x and it hits all of the delta y. I have conduction from node 11 to node 8. The conduction from node 11 to node 8. This is the total heat transfer on node 8. from 11. Okay? This is going to be delta y. So from node 11, what can I see of node 8? I can see all of its delta x. No, I can't. What the space that I have to travel through? All I have to travel through is delta x over 2. Delta x. See, it did it again. This is highlighted. Oh, it's highlighted in light blue, not dark blue. Okay. I can see delta x over L. Alright. Delta x over 2L. And I have to travel delta y to get there. Alright. There's another mode of convection, of conduction here. Or it's another mode of heat transfer, and it's convection. And it is H. Yes. H. And it's T infinity minus T8. Delta x over 2L T11 minus T8 over delta y. Delta x over 2 times L T infinity minus T8. That's from the bottom. Now from the left side, I have K T7 minus T8. It has to travel delta x, but how much can it see through the material? Only delta y over 2. So we write that. Okay. Here, T9 minus T8. So not someone would know. I think someone's rubbing something. This is going to be another convection term from the left. This is a y now. It can only see dy over 2 L, and it's T infinity minus T8. This is our nodal equation for T8. That's node 8's equation right there. Alright. It's quite small. This is gonna suck to solve for, man. Man. That's hard. The nodal equation for node 8 is thus. And then we put that there. Right. And then now for node 14. Node 16. This is the last node. All the other nodes are solved for. This is the last node. Okay. I'm just going to put 16 here in all of them. To start off. Okay. Alright. And now, what we do is we say K dxl 3 minus 16. The equation for node 16 is thus. So, no, what's that? So, let's see here. Where is that? Okay. So let's see here. Node 16. An hour 18. Okay, that's fine. Alright, equation for node 16 is thus. Okay. From the top, I have one of these things. I'm gonna take the bottom one because that has the dx's and stuff, but I'm actually gonna take its plus sign too. Alright, it's gonna be messy, but it's fine. So k dx over 2 is being hit from 11 minus 16, and it has to travel delta y. I also have h, I have convection hitting node 16, that's delta x over 2 from the top, and hitting L. It's hitting delta x over 2L, t infinity minus t to 16. That actually just fits. I don't even have to change that. This is the conduction coming from the right, so this is no longer T3, this is T17. It hits all of delta y, and it travels delta x. From the bottom, I've got something that hits all of my delta x and travels delta y, and it's tone node 21. From the right, I've got this big guy, and it's traveling delta x. Okay, so I'm going to get rid of this one. And it's hitting, so half of it hits half of the, oh, that's a problem. This needs to be inside. This needs to be there. That's a huge, it cannot be messed up. That has to be there. And that's for both of them. Okay. You can't have that. Those are not. That cannot happen. Okay. Okay. So from the left, I've got delta y over 2 of 16 being hit by T15 minus T16 as traveling delta x. Delta y over 2 is also being hit by convection, and that's 0. Save. Okay. This is the this is all that I've got written. That's just insane. All those equations to just describe this thing, and I have to freaking solve them all. Oh no, dude. Oh no. I really don't even know how I want to do this. I mean, do I just go one at a time? And just go really slow. I don't know what else to do. I really feel like I want a new Word document to do this in, because I don't. Man. So what I've got to do is, for example, this is node 1, right? So what I've got to do is, I guess I'll show you. So what I'm going to do here, I'm going to take all this, for example, I'm actually going to reduce its font like by a lot. Just make it 6-point font. Got a lot of room to work with here. Okay. Right. Okay, so what I've got to do is take the delta x and move it over. So how am I going to do that? I think what I'll do is do this, and then this becomes this, and then this has to go in brackets. Oh, come on. It has to load them all. Alright. I do that, and then I have to do this a bunch of times. Oh my god. I copied it. I just hit Control C. Okay. And then I have to verify. Okay. And then I have to say, I have to get rid of this. And then I have to say this plus this T2 okay, and those are the same. So if I do this and cut this, and then I just leave that as, I put it, and I put T2 on that. No, I did too much. I'm getting lost. Did Cookie would have some cool metrics to show me here to make this really simple. that I just do not know. I could look in the equation and just say what's all the same. Everything has a k on it, so let's get rid of all the k's, right? Everything has an l on it. Everything has a 2 on it. Okay, this is an easy way to do it. This is actually kind of nice. My stream is public, right? It should be. Okay, so now what I'm gonna do is T1. Okay, so what are my like terms? I have to combine all my like terms. So here's a T1. So I'll put that up here. Here's another T1. I'll put that up here. I'm going to take all my T1s, and I'm going to put them over here. Yes. Sorry, babe. Sorry, this is super delayed, by the way, so I like just texted you, but you're probably not going to see this for a sec. Anyway, alright, anyway. My girlfriend's on here. Let's see, so I've combined all my like terms for T1, T2. I have another T2 over here. So let me grab that and put it here. and now I just put a 2 on this, and then take this away, and then I just do, oh no, don't make me do this. No, you can't, oh come on, no, you can't do this, come on. You're serious? You're serious? Oh, that's terrible. I just want to get rid of the T1, that's it. Okay, and then now I can take all of this stuff only, not the why is it this is the, this shouldn't be in here. It should be outside of it. There we go. And now I should be able to, yes, okay. Oh, I hate this so much. Okay. Now I put that in brackets. This is node 1. Let me clean it. I have 2 of those. Goodbye. Oh my gosh, please. This is node 1. If I'm probably just gonna leave it like that. This is node 1. Yeah, this is node 1. Okay. I have to save this. I mean, where do I want to save this at? No, I don't want to save it there. Save it, copy, browse. I'll put this. I will put this in, I don't know, product 2. So I'll say like project to equation manip. Okay, good. This is node 1. Okay, node 1 done. Let's go get the next one. Node 5. Alright, same thing. Super small to 6. Now the question is, do I want to get rid of the, I think we get rid of this, right? And I just say node 1, and then I say node 5. No, not yet. Not yet. Okay. Alright, and I just do the same thing. Okay. This delta x goes here. These go here, and they get brackets. This delta y goes here. These go here, and they get brackets. This delta x goes here. These go here, and okay. This goes here, and they get brackets. Right. Okay. This and this are exactly the same. So you know what I'm going to do? Take the 2 off of that. Alright, cool. Now, I have k in both of these, so this goes away. I have L in both of these, so that goes away. I just realized I'm gonna have... Okay, so hear me out. So when I do when I'm changing K to find different how temperatures change via different conductivities, that is only really going to matter temperature-wise in steady state when you have convection present in a fraction of control volume, because if you don't, all of your K's cancel. Like, look, here, they all can't... This doesn't have a K in it. All the K's cancel. All of the lengths cancel. All the dx's and dy's would cancel if that was a thing. That's okay. Oh, Celeste, here, I'll show you what I'm doing here. If I have the... Yeah, so... This is the problem statement. So, essentially, there's these chips, these computer chips here, that are being pushed by this spring and housing, and that are conducting into a cold plate. Okay, so the idea is this is the cold plate, although there is interest in operating high power levels, blah blah blah. So you have a heat flux coming in from this housing thing, and you want to have the temperature in the cold plate up here that's having water in it not exceed 40 degrees Celsius anywhere. So how I've drawn that is, here's this. So you have the water cooling channels here, and you have the cold plate casing surrounding things, and we've drawn lines of symmetry here that we can just use to stack multiple things together because they're the same. And what you end up with is this thing, and we've meshed it with these nodes, and the distance between the nodes in the vertical direction is 4 millimeters, the distance between the nodes in the horizontal direction is 2.5 millimeters, and we just do an energy balance on a control volume that surrounds these. So those look like this. So for node 1, you can see I have the distance between node 1 and node the control volume width between node 1 and for node 1 would be half of delta x, because the other half is we consider symmetry, so it's adiabatic, so you basically just treat it like insulation. And then the bottom, the depth of the control volume is delta y over 2. So the conduction from node 2 to node 1, basically we do an energy balance on node 1 to find the temperature at node 1. For conduction from node 2 to node 1, we essentially say that node 2's temperature is conducting to delta y over 2 times length into the paper of into node 1's control volume, and node 6 is conducting delta x over 2 into node 1, and node 1 also has a ghost node 2 that's on the other side that conducts into it, and that sees delta y over 2L, and it conducts at a length of delta x. So that's kind of the way we do it. A lot of the equations are the same, so I've made this little drawing to illustrate just how the different flavors of the equations, and I've solved them in blocks. And so I have 2 Word documents here, and these are all of the equations, and these are all written out. We know they're right. So all of these are done. This is all 28 equations. And as you can see, node 8 and 15 are quite weird because they have, and these are 8 and 15 here, or 8 and 16. These have, coming from node 7 for node 8, for example, it has half of its control volume is experiencing conduction, and then the other half is experiencing convection from the water. So, yeah, essentially we're going to change materials. We're going to change the coefficient, conduction coefficient of the material in order to see how high of a heat flux we can get without any of the nodes reaching 40 degrees Celsius in the in the material, or yeah, just throw out itself. So right now, what I have to do is get it in matrix form, because what we're going to do is, now that I have all these equations, like, I can't use it in this form. There's just nothing I can do with this. What I need to do is have them more so in this form, where you have coefficient times temperature, coefficient times temperature, coefficient times temperature equals constant. And that way we can do a system of linear equations, and those you can solve with a matrix like this. So that is the procedure. I need to draw schematics still. I still need to put all of this in MATLAB. Like, I actually have to code this whole thing with all of its coefficients and everything, and then I can generate plots, and then I can discuss it and all that stuff, and I have to do this before Monday. And I have 28 equations that I have to put in that form. I've just done node 1. I'm about to do node 5, and I'm not even done with node 5. So wait, this is node 1. Okay, I'm doing node 5 right now. Yeah. So essentially I take this guy and I put him here and here. I take this guy and I put him here and I put him here, and then I take all of this and then I replace this bracket, and I take all this, or all of this, and I replace this bracket. And now I realize, so this, I kind of move things around now, so this goes here, right? And then I can take this T5, I can take away and put brackets on this thing, and add it here, and now I have it in the form that I want. I have not coefficient times temperature plus coefficient times temperature plus coefficient times temperature equals constant. And this is node 5. So now I'm going to write node 5. And now I do this for all 28 equations. And we just keep on going. Yeah, it's oh, it sucks. Alright, node 24. This I'm going to take down to 6, and then yeah. Okay, so this 25 is a ghost, but it's the same as T25, so we'll leave it. And this, oh, so the heat flux is my constant. I'm going to move it right now. Okay. This delta X gets moved to here, and then this gets control X, control V, and then gets brackets. This delta X gets moved from here to here. This gets control V, and it gets brackets. Okay. To highlight it again every time. That's great. Alright, this delta Y goes here. These get control C and control V, and these get brackets. Alright. I now take this guy, and I notice, oh, so I can't cancel K anymore. I can cancel L though, so L is the same everywhere, right? L is on all of these terms. There's a division by 2 in every single term. Oh, this is just delta X now. Okay. Alright, and that's all I can cancel. I can't cancel anything else. Okay, so now I see I have a 25 minus 24 here. When does a joke become a dad joke? I just wish there wasn't so much delay. There's a lot of delay here. This is a good question, though. This is a very good question. Let me get a phone stand so I can actually, like, see messages coming in. When it becomes apparent. Okay. Alright. Okay. I did not know. I didn't see that coming. My God. My God. I see. I am being tortured. Okay, this guy goes here and nope, not there. See that T being highlighted? That's bad. You want it outside, because if you don't, you will screw yourself. Okay. Here's this. Now, see, remember what we were talking about? This is the same as that, which means that I would have put a 2 on the outside of this when I put both of these in here, and it would have been the same. No? Remember that? Well, that's what we're gonna do. Oh yeah. Oh yeah. Oh yeah. That X, get out of here bracket, put it in there. Alright. There we go. Likewise, this comes here. This gets X'd. And we go outside here, copy all this, get rid of the bracket. Okay. So now I take the T24 and I put it here, and then I take the T24 and I get it out of here, and then I put a bracket here, and then I say minus. I say plus, excuse me. Can't make those mistakes. Just that alone would totally screw up the solution, and it's so hard to debug. The way I'm doing this, it's so hard to debug. So, yeah. Let's see. 24, 25, 19. Okay. So this is node. Oh man, I have to be really careful to make sure I don't get lost on what node I'm working on. That actually makes a lot of sense. This is node 24, but I wouldn't know that unless I highlighted that. So I'm gonna start being real careful in how we do this. Okay. So node 1, 5, and 24, I'm probably going to start putting these in numeric order so that I can see what I'm doing here. But, oh my gosh, these constants, dude, this is going to be awful. So basically this would be my index, and then these would be this would be my row, and then these would be my columns. So on row 24, column 19, this is on my coefficient matrix, that's my coefficient. On row 24 of my, and column 24, that's the coefficient. And it just, out of the bathroom, out of the bathroom. Excuse me. I actually super glued my chair trying to fix it, and it did not even hold. Wish it would, but it does not. I'm gonna try it again. Alright, I just squirted a lot of super glue on this thing. So hopefully it actually holds this time. Okay, I honestly don't see how I'd fix this. Like, it's a nice chair otherwise, but yeah, like, the armrests underneath, they really cut into the material. So, if I got another chair, I'd want it to be like a leather thing. Just a wet glue there that hasn't touched anything. So there's a big cavity. That's what that means. That's why it's not gluing onto anything. There's just a big old cavity there. Nothing for it to hold on to. Huh. Alright, well. Going. What are we doing now? Node 28. Oh, this is gonna be so freaking hard to debug, man. But what else am I supposed to do? I have to do this fast now. I don't know how I would do this without extreme precautions and not in debugging. I have no idea. I hate how I've had to go. There's no shortcut for this. You know, bracket button. You just have to do everything so manually. It sucks. Alright, I'm just gonna get rid of this. 27, 28, 27, 28, delta y over x. Yep. Get rid of that. And then get rid of this too. Move this over the other side. This delta y. all the L's can go away now. Delta x over 2 delta y. This goes here and here. X e. Okay. All right. Okay. 28 for node 2. Okay, so here's the thing, right? Here's the thing. Nodes 2, 3, and 4 are nice because schematic here. 2, 3, and 4 are nice. Why? Because they have the same boundary conditions. So once I solve and simplify the equation for node 2, all I have to do is change the numbers of the temperatures in order to get nodes 3 and node 4. It's quite simple. So that makes it really nice. We're going to do that. That's the same for all the colors, except green. Green, like node 23 and node 19, they're fairly similar. I did not really, what is it? Node 23 and node 19 are fairly similar, but they have different conduction directions. They're not directly comparable, but they're the same kind of flavor. So, and node 15, 11, and 7 are they're really their own color. They really should be their own color, but I wanted as few colors as possible. So 1, 2, 3, 4, 5, 6, 7 colors. Really there's like 9 or 10. But it's not too bad. Okay, so node 2. Let's get node 2 in here. I'm excited for node 2. Let's get node 2 a round of applause coming in. Node 2. I don't know how to get the static off my mic. Wish I could. Okay. Well, it's all the same. Everything has K. Get her out of here, K. What happens? What about the L? Yep, there's L's everywhere too. Get rid of the L's. There's only a 2 in 2 of these things, but one of them we'd be able to get rid of, but not the T3 and T1 version. So, okay. Take this guy. Wait. No, that's not really what I do. I just needed to do it. I need to do it right. Oh, come on. Every time I load into Word, it makes me reload the fraction thing because it refuses to store it in the cache, and I don't know why. It's terrible. Okay, there's that. I've evolved another method of system, so instead of taking this out and then doing this and then putting it in brackets, I'm just going to immediately distribute it. So I take this, go X, go V, take this guy, go X, highlight the fractional component, take this guy, there, and there. There we go. Everything's distributed. Alright, now we combine like terms. So here's T2, Here's another T2. T1 is gonna go before T3. T1 and then all these T2s are gonna go in between T1 and T3. Okay, so this is how we're gonna set it up. Yep. Alright. And now I notice that this and this are the same. So I'm gonna put all of this stuff in brackets, and then this T2 here goes away, this T2 here, this T2 goes away, and now I just distributed this. And then I'm gonna say, instead of the 2 being here, it's just, we're just gonna do this. Okay. Alright, so there we go. That's that. Okay. This is node 2. This goes in between node 1 and node 5. Okay. Now, this is node 3, node 4. I have to look at my equations here. Node 2 is this. So I literally add 1 to everything. So T1 becomes T2, T2 becomes T3, T3 becomes T4, and T7 becomes T8. Node 4, this becomes T3, this becomes T4, this becomes T5, 7 becomes T9. Right? Should be, it should be it. And 7 becomes 9. So 3, 4, 5, and 9. Yep. Yep, that's node 2, 3, and 4. Okay, so I have nodes 1, 2, 3, 4, and node 5. Okay. Alright. So there we go. Okay. Now, what we're going to do is another node. Node 2, 3, 4 is done. Node 10. Okay, so looking back at our little picture here, node 10 is going to correspond to, so we have 10, 13, 18, and 23 that I want to do now. I need to look, so when I'm doing 10, 13, 18, and 23, node 5 becomes node 10, node 10 becomes node 13. Okay, I need to figure out how to translate the numbers because it's not just adding 1 anymore. This is a two-dimensional problem and this is not easy, so let's see. And you're not adding the same amount every time either because you have that big break in there. Does that matter? I don't think that matters. Yeah, 10 isn't interacting with 8 in any way. Or the stuff that comes before. Oh no, it changes the numbering system. That's why. So let's say I solve node 10, and then I say, okay, for node 13, T5 became T10, T10 became T13, T9 prime became T12 prime. Okay, so I can do that. There is a way. Alright. But there's a way, and I can make a will to get that way. Alright. So, node 10. Alright. Node 10 is this giant, oh, did not mean to do that. It's this giant behemoth of a guy here. 6. Okay, node 6. Okay, node 10. Okay, so doing the same thing. Get rid of this guy. Let's get rid of all the junk first. So we have all L's everywhere. Get rid of the L's. K's everywhere. Get rid of the K's. Yep. Okay. And alright, so the delta y comes down here. Copy this stuff. Put it down here. And then get it to T10. Same thing here. This guy gets this fraction on it. Okay. D1, okay, D1, okay, dx, so this guy here, I'm gonna do fraction, bam, x, it's like zoned out for a sec. Okay. So T9 I want to go next to the other T9 over here. Why do I have T9 twice in node 10? Oh, that's why. Alright, I remember now. Okay. All this stuff, put it in brackets, add a plus sign, get T10 out of here, get this temperature out of here, get this temperature out of here, copy this stuff, put it in brackets, get T9 out of here. Okay, I'll just add a 2 here. Okay. Get rid of this 2, get rid of this guy. Add a 2 here, and get rid of this guy. Okay. That's node 10. There we go with node 10. Yep. Now, node 13, all the T5s become T10s. Okay, so all the T5 becomes T10, T10 becomes T13, T9 becomes T12. And T13 becomes T18. Alright, so there's that. There's node 13. Node 18. Alright. All of the 13s become 18s. I don't want to do that yet. 13. All of the 13s become 18s. The 18 becomes 23. Okay. The 18 becomes 23. So this becomes 23. All of the 13s become 18s. All of the 12s become 17s. And all of the 10s become 13s. Woo! This is tough. This is like actually tough. Alright, node 23 now. Okay. Node 23 becomes node 28. Node 18 becomes node 23. Node 17 becomes node 22. And node 13 becomes node 18. Alright. Very nice. So, there's node 10. We'll go... node 10 will go after node 5. Node 13... I can actually just put all these here because they're all grouped. Okay, so I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 of 28 equations. Oh my god, I'm not even halfway there yet. It's been an hour and a half, dude. How long have I been streaming for? This is all I've been doing while streaming. Like I've had everything else pretty much. 2 hours. 2 hours. Oh. Holy crap! I'm gonna write the report for this thing. My gosh. All right. Okay. 19 is unique. Yeah, 19. The next 3 are unique, and then I have a big break. So let's do the next 4. as unique equations. Okay, node 19. L L L K K K K. Can I just? No, I don't think I can. Oh, what am I doing? I'm like second guessing myself here. Oh no. Oh god, are you kidding me? Are you serious? I'm pretty sure this is right, but I don't know. Okay, no, that has to be right. This has to be right. Negative this minus this equals -2. I have 2 of those. And I have 2 of these. Was there any representative here? Hang on. Invalidate. There's no way to generalize it comfortably. I could maybe do it, but there'd be so many errors. There's no way to tell. This is right, though. This has to be right. I know that I'm not gonna get the right solution. There's just no way. It's really sad, man. I know it because there's no way to debug. If any one of these equations could be wrong, and I would have no way of knowing because there was no simplification factor. But I mean, like, I can't just go through and have pages and pages and pages and pages and pages of simplifications. You can't have just 5 pages of just you simplifying equations on paper so that you can go back and look. And even if you did, that wouldn't help you find it. There's no way to debug this. There's just so many nodes. I don't even have time to run a SolidWorks simulation for it. It'd be nice. Alright, now we're going to do node 11. Please do not. Okay, so this is our first convection one. There's still L's and everything, but the K's don't go away this time. Now the K's matter. So, I take this guy, put him here, take these guys, get rid of this fraction thing. Okay. This guy goes here. Now let me do it right. Delta x, delta x, delta x, delta x, delta x. Put this here. This guy. Goes over here. I just realized. Did I freaking do that wrong? Up here? Oh, I mean, come on. Yeah, I did. What? Does 25 has it? I know 24 has it. That's it. Okay. I just, man. Okay, that's why. No, still doesn't work. I'm simplifying wrong. I think that this is a delta x, not a delta x over 2. And there's no way for me to check it. With the other one there was like 7 equations, so it was easy to just simplify it all. And even then it was like 5-6 pages of just simplifications. But with 28 equations, there's no way to do it. There's no way to have a comprehensive. What do you have? 50-page report? There's no way. I don't know what else to say. I mean, you take all the 2's out. What's the difference between 24 and 28? It could be as simple as having that 2 flipped. That caused everything. Because you see how this, the 2's on the bottom, you got delta y over delta x, and this 2's on top. Well, these 2's are on bottom, and so that would make sense why this is still here. But they all have the same conundrum where it would be just simpler to just say, hey, everything is the same, everything's delta y, whatever. Everything is divided by 2. Alright, well, let's check this. So that's what it is. No, that's what it is. Okay. This is right. It's just, it's in a really stupid format. I'm gonna change it now. This should have a 2 on it. This should not. This should have a 2 on it. This should not. And this should just be delta x. That's it. I'm even going to do this. And now they are like the same format. Okay. I'm okay now. Alright. I have taken this thing, I've simplified it out, moving the constant over. I have my T11s over here. I'm going to move my T16 over here. Copy your plus signs, please. T11, T11, T11. There's a T11 over here, okay. Eight, and then 12 does not come after this, so 11, 12, T16. Okay. I take all of this. I put it in brackets. I add a plus sign. And I say, get out and get out here. And then I have 2 of those, right? So this goes away. And then there's that T12. Why is there another T11 there? Okay, it was. It is. It's fine. Okay, it's right. There's T12. Okay. Take all of this, apparently. Put it in brackets. Put this here. And then subtract. When this guy goes away. That guy goes away. This guy goes away. I have just one of those. So y minus x, x minus over y, minus h delta y is T11, T8, T12, T16. Okay. Alright, that's node 11. Okay. That comes after node 10. Holy crap, dude. Chapter 11, and then we do equation 15. Okay, this guy goes here. This guy X V. No. Okay. Same thing. This guy X. Do this V. X V C V X V X V C V X V C V. 15. Alright. Node 15. What is this? I don't know what. Okay. 15 goes here. 20 goes back here. 14 comes before 15. And this guy goes over here to become a negative. Oh no, that's what I was checking with these things. I was checking if these should be this. I forgot about that. I gotta check that. That's bad. Alright, so is this right? This is okay so far. No, it's not. The 16's in the wrong spot. Take your plus sign, please. T15, T16, T20 is that. There's an L everywhere, so I'm taking out the L's. Forgot to do that earlier. Shit. Oops. This goes here. Okay. Okay, well that's it. Alright, so now I need to check this, because that's a big problem. If that's the case. So we can't have that. So if Q double prime is positive, then node 27 must be negative. It's not. So this is negative. I'm pretty sure I did it on the other one too. Yeah, see, you don't put the negative on that. You put it in front. I hate Word so much because of the way it writes its equations. It's just awful. Alright, here's this. Yeah, that is node 15. Okay. Node 15. X 13, 18 goes in between those 15s here. Alright, how many do I have now? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I'm halfway there. Halfway there. Okay. So now, with all of those equations, we just stopped at node 15. Now we do node 7. What is node 7? Did I do node 11 already? I did. Okay. Node 7 is the other hard one, and then 9 through 22 should all be quite nice. They all come together nice. So 1, 2, 3, 4, 5, 6 equations. That should be really sweet. So, alright, node 7. One, two, 6. Alright. Okay. Oh, I need to get rid of the L's right now. But I do. There's L's and everything. There's not, the K's don't cancel, so I can't get rid of the K's, but I can get rid of the L's. Okay. Right. Okay. So 7. What's the highest number? Okay, so this first thing first, I'm going to do this. X, put it over here, and make it negative. Alright. 8's the highest number in this, right? Yep. 8's the highest, so 8 goes over here. And then it's 6 goes here. 7, 7, 7, 7. All the 7s. You get tacked into a bracket. addition on them, and then we get them canceled out. Okay, so this goes away, this gets out of here. Alright, I'm just gonna reorganize this because I don't like the way this is written. Alright. Coefficient T2, coefficient T6, coefficient T7, coefficient T8 equals that. Alright, it's not too bad. 7. Grab 7 and put it after 5. Okay, there we go. That's 7 done. Alright. Oh, those are one of the biggest ones. Alright, save. Back them again. Oh, come on. Okay. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14, 15. Right. L's everywhere. Get rid of them. You don't have a delta. You don't have a K on you either. Why? There's no K here. 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 There's a K there because I changed it. Come on, dude. What the heck? What are we doing? Alright, node 9. Okay. Node 9 has no K's. All the K's cancel. Okay, I don't like the way this is done. I have to do this. Oh, I don't have to do this every time though. Get rid of this too. Okay. Actually, let's do this. Oh my gosh. Okay. 8 comes before, so 4, 8, 9, 10, 12. Those are the equations. So 4, 8. 8's next, so 8's here. 4, 8, 9, 10, and 12. Take all the 9's, put them in a bracket, and then take away the 2 9's. Alright, we got 2 of those and 2 of those. Okay. Yep. That's that. Alright, this is node 9. Okay, so that's node 9. So if I were to do node 9, let's look at my diagram here. Node 9 and node 12 have the same equation. So we do 9 and 12. The node 12 is going to be so 12 becomes 17. So this is node 12. For the 12, the highest number becomes 17. The second highest number, which is 10, becomes 13. The third highest number, which is 9, becomes 12. And the second lowest number, which is 8, becomes 11. And 4 becomes 9. Wouldn't it be better to do like this? And say node 17. For node 17, the 12 becomes 22. Yeah, I think it's better. The 10 becomes 18. The 9 becomes 17. And the 8 becomes 16. Plus sign here, and do you need that? Okay. And the 4 becomes 12. Alright. The 12 in equation 20 becomes 25. The 12 becomes 25. Okay. The 10 becomes 21. The 9 becomes 20. Oh my gosh. Nine becomes 20, the 8 becomes 19, and the 4 becomes 15. Alright. Damn, I had just a full page of the small the smallest way I can write these equations. Alright. Now for node 21. That was 20. Okay, so node 21. From node 20, I guess, the highest number in node 20 is the 25. So 25 becomes 26. Oh no, I have to do from node 19, from node 19. Alright. The node 12 becomes 26. Node 10 becomes 22. Nine becomes 21. 8 becomes 20. And 4 becomes 16. I just realized I can just do them in reverse order of their size. So I'd say for equation 22, the biggest number in here is 27. After 27, 23, nope, 23. Let's do 23. And then after 23, at 22, there's a 22. There's 17. Yeah, that doesn't look either, does it? Alright, from node 21, 26 becomes 27. Okay. 22 becomes 23. 21 becomes 22. The T20 becomes 21. Oh, they do have a 21. I didn't see the 21 there. That would work. And then 17. Yep. Alright. So that's that. Okay. So now I put them in order. So node 9 I have to put up here somewhere. So node 9 goes after node 7. Node 12 goes after node 11. Node 17 is that before node 18. Node 20 goes after node 19. Node 21. Uh-oh. I bet you this is node 22. Yeah. Okay. Alright. Almost screwed myself. Okay, 21. There's just no way to debug this. This makes me so sad. I know the solution's not going to work. 20, 21, and 22. 23, 24. Okay. So here's just a full page of all the equations, and I can't even fit them on one page at 6 font with a font of 6. 1, 2, 3, 4, 5, and then some are missing. 6 is missing. 6, 8, 16, and 14 I know are missing. So 6, 14, 25, 26, and 27 are still missing. 8 and 16. Oh, 8 and 16 are going to suck. 6 and 14 are also going to suck. And then I have to write all these out. Oh, God. This is supposed to be... This is like 35% of my fucking grade. What do I need to get on this assignment to pass? I'm fine. Check. Depends on if he's graded assignment 5 or not. If he hasn't, I have no way of knowing. There's just no way to tell. Oh, this is 45? Hold on, let me check this. So I need to get a 70 or higher. Oh no, I need to get a 67.7 or higher on this project. I can do that. I can do that. That should be fine. Even if I can't get the right solution, which sucks. I can still get it. Because even getting a completely wrong answer, oh man, if I get like a freaking wrong answer, like a super wrong answer, dude, that's gonna be bad. When I turned in one assignment and it was particularly really terrible, because I just had a super hard time with it, and no one in the class solved it right, except like 2 people. But even turning in a wrong answer and a really terrible report, I got a 60. I only needed a 67, or I need a 68 on the project in order to win, and I'm getting all the equations, and I know I'm doing it right. I feel good about this, you know. I tried doing iterative Gauss-Seidel techniques and all kinds of weird crap, but for this, I know what I'm doing. We are fine. We're gonna be alright. We're gonna be alright. That's really nice, actually. He gave me an 85 for Project 1, even though it wasn't right. And even though, well, Project 1, no. Project 1 was right. No, Project 1 was good. Then I wrote a decent report. It wasn't great. It was alright. So, I need a 67.7 to pass. Just to pass the class. As long as I pass, I'm good. And even if I did get lower, I'm pretty sure he wouldn't fail me, because that would suck. That would suck bad. And then I wouldn't graduate. But, nah, I mean, we know how to do this. And we're already writing the report, we got schematics and stuff. So, how many equations are missing? So, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. I have 6 remaining equations to do. Okay, and those equations are node 6, node 14, node 25, 26, 27, 8, and 16. Let's do 6 and 14 right now. So, node 6. Once I finish node 6, I'm probably going to take a big Gungeon break. Because, yeah. Probably just going to take a huge break. And then I will come back, and then we will do the coding for this thing. Because we need a code today. We have to code today. Right, so same thing. Delta y comes over here. Before I even do that, are there L's everywhere? There are. So this is node 6. So 6 is here. Okay. Yeah, we have convection here. So it's L, 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 L. Okay. Delta x can go here. Delta x can go here. T7 and T6. Get rid of this. Put this here. So the prime can go away, and I take this guy. Control C, Control V. The brackets can go away here, and then I can take this guy and go Control C, Control V. I can take this guy here, get him away. C, yeah, no. Control C, Control V. This guy, Control X, Control V. Control C and Control V. That is right. Okay, so now that we have this done, we're gonna say T1. Oh, first thing I'm gonna do, take this guy and put him over here, and make him negative, because I know he needs to be negative. All right. Is there a 2 in the denominator everywhere? Yes. Yeah, there it is. I'll do it later. I'll do it later. 2, 7. Okay, so we have T7 twice. Is that normal? Yeah, because we have a ghost. Okay, so T7 goes over here. T7 goes over here. Take your plus sign, please. Okay. I have 2 T7s, so I'm just gonna do this. T6s are all together. So all these get brackets. And then I just start deleting. Okay. Alright, I've got 2 of these. And this can go in the back. And this gets added. Okay. Now this becomes just dx. Put a 2 here. This just becomes dx as well. Put a 2 up here. And take this 2 away. Take that 2 away. Alright. There we go. That's node 6. Very nice. Very pretty. Put it in my collection. I think the first time we rolled over to a new page, yep. 5 left. Node 14. This is the last algebra I'll ever do as a college student. This is insane. I'm a mechanical engineering college student at a master's school university. 6. Okay. Now. Okay. Okay, so I've got L everywhere. T infinity. Okay, so this guy gets. Let's do this again. There's a division by 2 everywhere. I'm gonna just do that right now. Take this guy. Okay. This guy, Control C, and here Control. Okay. Control C, Control V. Okay, no, that does make sense. Alright. $15. Take your plus sign, please. Comes over here. 19. Goes behind 15. Nope. Goes behind 15. 14, 14, 14. There's another 15 here apparently. And take your plus sign. What? Take your plus sign, please. This guy is over here, becomes negative. And negative h, okay, t14, 14, 14, 14. Copy all of you. Equation, bracket, and then get rid of 14s. Why would you do that? Why? You're kidding. Go away, please. Two of those. Go away. And this moves in the back. Fifteen, 14, 15, 15. Why do I have two mirror? Don't even need to look. You got a mirror. I should have known. No, no, you're not. There's no way. There's no way. Thank you. Oh my gosh. Okay. Node 14 is done. That took forever. Alright. Node 14 is done. After node 15. Or before node 15. There we go. Yes, very pretty. Very nice. Alright, 14, 15, 19. Okay. Cool. There's a lot of linear equations, dude. Okay. Hey, I'm gonna need more coffee. This is a lot. How long will we been talking for? 3:23. 3:23. That's pretty good. So how long have we been doing equations specifically? Equation simplification. We started doing equation simplification probably like right at like an hour 40 minutes ago. So it's gonna take me it took me 2 hours to do all of this. So that's really not that bad. That's actually pretty cool. I don't know if that bodes super well for the coding part. I feel like the coding part is gonna take maybe 3 hours, and then the report itself probably would take another, depending on how long I can work on it, probably another 5 or so. I'm gonna have to get up at 6 and do this, assuming I don't get the code done today. Oh no, I have to get the code done today. The code has to be done today. The code has to be done today. The code's got to be done. There's no way we're just getting up at 6 and then starting to code. There's no way. Oh, it's gotta be done today. Okay. 4 left. The equations that we have 2 left. We just did node 14. I don't have 5 left. I don't have node 25? I do not have node 25. Oh, 25, 26, and 27 are concurrent. Oh, dude, this is gonna be nice. Alright, cool. So, let's get node 25 in here. Node 25, 6. Okay. 25. Alright, L's everywhere, right? Yep. Get out out of here, dude. Division by 2 everywhere? No. This guy immediately is going over here. And he is not positive, he is negative. Okay. Instantly. Okay. Now. Okay. Yeah. I'd like to do it, but I can't. So. Yeah. 20, 20, okay, so 24 goes in front. 20, 24 goes in front. 25, and then 26 waits. 5, 26. Alright, nice. These are handy. Gosh, I should have learned LaTeX. I did not know this class was going to be like this. I thought it was going to be, you know, oh, you're doing Navier-Stokes with stuff, and you have to do homework on, you know, so I don't know. I did not think it was going to be a bunch of reports, though. There's just been reports like this, where, and some of them are harder, some of them are easier, but it's just been reports. At least 13 pages. And they're not, it's not like so bad, but you can see like the thing I'm working on now is 27 pages long because I have my other report that I'm stacking onto it because I wanted to have a comprehensive feel, but like I'm not going to use any of it. But just the report that I'm doing now that I've already got is what we're not even close to being done yet. We've just written out our equations and we're at page 12. I haven't even solved them yet, nor have I talked about what we're even going to do with them as far as the viewer is concerned. So this is going to be a 30 pager. It's just, yeah, it's just going to be, it's going to have to be. And formatting alone is just going to take forever. I don't know if I'm going to care too much about it. I really just want to take the 70 and leave. I'm not. It'd be nice if this, it'd be nice if I could get a higher grade, but I just don't. This class isn't what I thought it was. I'm just not passionate about CFD. I'm not. I think it's a neat concept, but if I was going to use CFD in the real world, right? Let's picture this, like this is going to read CFD in the real world. I have to go find all my coefficients. That's the problem. Because he'll say here, it's like, oh, you got so-and-so, you know, watts per meter squared of heat flux. It's like, okay, well, let me do, you know, I wonder if my Arduino's heating up too much because I'm doing something. Or maybe I'm worried about this heat sink on this block that I've got it put on that's on an SSR. If this gets too hot, what, you know, I want to make sure this doesn't get too hot. You have to look at all of the components inside the SSR made, like, in order to kind of figure yourself out, or you have to measure something. You have to, like, do experiments to find things. You know, and even then, it's not going to be, like, how do you know if it's right, other than just doing it? You have to do this whole experimental thing. I feel like if there was another class with this, where you combine it with experimental methods, that would be really cool. Or that'd be a master's thing, because you know. So this class he was right. Like this is a taste of master's level work. If you hate this, then don't get your master's. yeah, I just feel like it's above me in a lot of ways. It's not that I can't do it. It's just I don't understand why I would want to. I don't know. Node 25 to 20, 24, 25, 26. Did I just solve this? Is this one done? Did I just do this? I hope so, because I'm gonna not look at this again if I did. No, I didn't. No, it's not done yet. This needs to be simplified. This 2 needs to go away. There's K's everywhere here. Oh. I just realized. For all D's, right? Oh no, I can't do it. Ah, dang. So some of these have H and K, which is really sad. That's a constant. No, it's not a constant. It is not a constant. Coefficient. Yeah, there's no way to make this any smaller. Unfortunately. This there is, though, because there's a K everywhere, right? So theoretically, this is this divided by K. But then you just have dy dx everywhere. Which I think is fun, but and I can multiply by 1 anytime I want. So for example, dx over dy, I can write dx dy over dy squared. I can always write that. Anyway, okay, so that's node 25. We're done. Now that we have node 25, you know what we can do? According to our little schematic here, which I'll pull up in a sec. Node 25, 26, and 27 are all the same color. They're orange. So what we can do is I can just rehash this equation for node 26 and node 27. Okay, so for node 26, right? I think literally everything just gets increased by 1. Yep, everything goes by 1. So 25, 20, 21, 22, 24, 25, 26, 25, 26, 26, 27, 26, 27, 28. Done. Alright. And all these are already in numerical order, so you know where they go. Bam. Nice. Alright. I have 2 more equations to do. Eight is missing and 16 is missing. And then I'll have all 28 equations. And then I can code. Man, I might get coding done today. And then I might get some of the rest of the report kind of formatted today, and then tomorrow I can drill schematics, and then write a nice discussion, nice conclusion, get the results, put some cool stuff on there, and in the morning, by then the morning will be done, and I'll turn it in. And then by the afternoon I can get ready and go to the pictures. Oh my god, that's beautiful. Beautiful. Absolutely gorgeous. Alright, equation for note 8 is thus. Here's the hard part about note 8. It's freaking huge. And yeah, it's massive. So I would love to work with it like this, actually. This actually makes me quite happy. And I can't zoom in more than this, unfortunately, but I can but yeah, I can see this. So okay, K delta XL. So L. Alright, first thing I'm gonna do is take this out of brackets, because I mean I get the brackets, but I don't want them in brackets right now. This. Okay? Alright. Is L in everything? Yes. So we're going to take L out. So L goes away, goes away, goes away, goes away, goes away, goes away. Fantastic. Oh. Oh, I didn't even... Okay. Sorry, I just messaged. So, we're still simplifying the... Let's see. Yeah, we were still simplifying those equations there for a little bit. Dang. Alright. I guess I should change the title. It won't end the stream, will it? Hopefully it won't. Okay. Good. Alright, it's part 2 of the thing, not part 1. Hopefully that updates. Yeah. Right. Alright. Cool. So, continue here. continue with this. I guess I'll do this first because this is gonna suck the most. But alright. C and then Control V. Okay. Alright, K, do you want very nice, very nice, very nice. Okay, this goes here. Here. In here. Oh, and this goes away. We don't want double that at all. Control C, go here, Control V, and then Control C, and then Control V. Okay. Take this guy, go X, Control V, Control C, Control V, Control C, Control V. Alright, this guy, Control C, and then I do this, Control V, and then I do this, Control C, and I do this, Control V. This guy is Control X, Control V, Control C, Control V, Control C, Control V, and this guy is Control C, Control V, Control C. Oh, shoot, we don't want that at all. Control C, Control V. Alright. This is the monster. So, now what we do. Copy things with signs, start organizing. First things first, I'm going to take this guy with his sign, because we don't copy things without signs in this town. Take this guy, because he's a constant, right? So, negative. Do I have any other constants? I do have another constant. His name is Henry. Henry is a negative guy, so he's negative. Alright. Do I have any other constants? I shouldn't. Okay, good. So 3 is 7. Okay, so 7 is smaller than 8, but it's in between things. So 7 comes after 3. And then we have 8, and then we have 9. And then we have 11. These are all my T8s, and it's a lot of T8s. So all of these T8s get put in brackets, and then we do an addition sign, and then I do this, boop, bop, boop, bop, boop, bop, boop, bop, bop, boop, bop. Okay, so with this over 2 stuff, KT3, KT7, T8, T9, T11, and then 2 T infinities. So for the 2 T infinities, I'm gonna say well, if I factor a T infinity out, I still get negative H. So, well, I'll just do that. So we'll try this. So I'll say I'll do this, and I'll take the T infinity out. And then I'll put the H here too. And then I'll take the H's away. And the negatives remain. Alright. So now I have, do I have k dx dy? I do here. K dy dx? I do here. I have an h dx over 2 and h dy over 2. I'm not going to use that. I'll back. Dang. Second to last equations. Man, Alright, ladies and gentlemen, as you can probably hear right now, my coffee is empty. I'm going to refill it. See that? Jeez. Everyone, so we can continue on our quest to solve these equations. Not solve them, but simplify them so we can actually put them in a matrix and use them. So, okay. HT infinity. This is node 8. We are done with node 8. I don't think I can simplify this anymore. What I can say is I have this, which is, you know, what's 1 plus a half? Well, I can say this, that instead of 1, I could say it's 2 over 2, right? So over here, I can do the same thing. I can say 2 over 2. I really have 2 over 2 dx dy. Alright, so if I do this, If I have 2 over 2 dy and 1 over 2 dy, what do I get? I get 3 over 2 dy. Then I can get rid of this. I can do the same thing here. Nice. And here I've got different numerators, but I've got the same denominator. I could say minus h dx plus dy over 2. Do I want to do that? I don't know, man. I guess I could. Why not? It's already in a bracket, right? And that just does look better, I suppose. So, I'll just... right? I feel like that, makes sense. And I can just take this guy and fix him out and put him button here. So yeah. Okay. Well, there we go. So this is node 8 now. This is node 8. Alright. Let's try to get him in 6. 6-point font. 1, 6. Oh, we can do it. He can fit. Oh, he fits. He's the long boy, but he fits. 6. Yeah, we're gonna save right now. Okay, node 8. There he is. Node 8 comes after node 7. Alright, there we go. Oh, I cannot wait to assemble my B vector, man. Or my A vector. Good lord. 28 equations, 28 unknowns. That's old. New copy. I can't wait to show you how I'm going to code this thing. Because I'm going to do stuff with the Arduino to print to serial so that I can copy all the lettering and paste it. Now, I'm used to Arduino IDE version 1.8, but apparently they've released like 2 point something and it's way different. You can actually make the screen dark, you can actually change the font size and all that stuff. If I do that, I don't know, man. This is a race. This is a race. I'm just gonna make sure I can pull it up. Arduino. I still have 1.8. Cancel. Alright. So Arduino IDE, I believe, is the new one. Yeah, this is the new one. Okay, and if I just open Arduino, just the Arduino app, does it give me the, yes, yes, that's what I want. This is what I want right here, this stuff. I guess I'll try it real quick. I'll plug in my Arduino and see if we can do something. So, I want to print to the serial I want to print to the serial so I can do things, but the code runs on the Arduino. So in order for the code to run on the Arduino, I have to do a little something called plugging the Arduino in. So I guess I'll do that. If I can find the cable, of course. If I cannot, we will use some. I'm gonna try the new. Or, you know, no. I'm gonna do this other equation first, and I'll do that. Got one equation left, dang it. And this is the last equation I'll ever solve. Actually, no, it's not. It's not nearly. I've got. It's the last big thing. This is the last time I'll feel like I'm in tough food. But no, after this, I've got. What's the last equation I want to solve? I'll oversimplify like this. I'm never gonna end like this again in my entire life. probably guessed. I cannot copy things from my computer and just paste it on the personal machine. Doesn't work, right? Because they don't have my clipboard. I have my clipboard. I have to send my clipboard to that in order for it to work. How do I do that? Via email. So let's log in my dang it, dude. So this all that, yeah, all this time. All right. I want to. Oh, I don't know. I have to like sign in on Duo Push and everything. So give me a sec. I've got it set up now. I can now send stuff to myself through the Outlook. And, yeah, so we got that. Alright, so to start coding, we're gonna save this script right now as CFD project. Can't put that. Project 2. Alright? And that's going to be in a folder called CFD project project 2. And in here we're going to have CFD project 2 save. Alright? Add to path. Alright, cool. So clear CLC. And now we can code. So probably gonna have some constants, so constants. Right. So what do we have first? I'm gonna put this here. And then I will grab the problem statement here. And we need to start inputting things. The constants. So dx equals 2.5 e negative 3. Okay? dy equals 4 e negative 3. So this is horizontal distance between nodes in meters. Okay, that's what I'm doing. This is vertical distance between nodes and meters. Alright. Cool. I would cut my mouth so salt hurts, but it tastes good. I have like 3 of these, you know? They're fantastic. Alright. UIDX, okay. Okay equals 160. This is conduction coefficient in watts per meter Kelvin. Excuse me. plus 273. This is water temperature in K. I'm gonna keep everything in Kelvin because I know Kelvin will work. T inf. Alright. And convection coefficient of H equals 4,000, and that's convection coefficient in watts per meter squared K. Alright? Okay. Those are all the numbers we need. That's it. That's all we got. So, that's literally it. Here's the hard part. I'm going to define a matrix A. It's going to be zeros 28 by 28. B is going to be equal zeros 128, and X is going to equal yet. So we just have to define these two vectors, okay? So here's the thing. Now we're going to go through Arduino and do this, and code this right. So I'm going to show you all how I do this. File new. I love how I can just create a new thing and it's super fast. Alright, void setup. Alright, so void loop. Void setup, serial.begin. Oh, this is fine. And void loop, I'm going to say for I int I equals 1. I is less than 29. I plus plus, and have that, and then I'm going to say serial.print A underscore 1 underscore no, I can't A underscore, this is a thing, and then I have to do serial.print I, and this is an ln. Okay, I just want to see what this does. Oh, it doesn't have an Arduino to run on. Hey, no way. It just works? Nope. No, it doesn't. It can't see the Arduino because it's not plugged in. Okay, here we go. Plug that in. This in. And we operate on COM3 or COM3 Arduino. Okay, let's try this. Yep. did it. That's it. That's what I want. Okay. I wonder if I can just say A11 equals A11 equals A12 A13. Okay. Try this. A1. No, I'm gonna copy this again. For int J. Gabriel's on J. That. And then A. Oh, excuse me. A. That. Yep. Print that, and then I, and then I'm not gonna print null anymore. I'm gonna print A, I, I'm gonna print a comma. Oh. Then I'm gonna print a J, and then you're gonna print ln this and that, and then you're right. Okay. Let's make the delay like 50. Alright. And then I'll lie. I was not declared. Yep. OJ. Nice. Okay, that's taking a long ass time. Let's do 10. Make it like 5 times faster. Yes. Okay. So, basically, it's when you say I want to set A11, A21, the row is which equation you're on. The column, which is the second number, is going to be which number you're on. Right? So we really don't want to go IJ, we really want to go JI. And instead of this, we're going to do this. And then I'm going to add a plus. Spaces. And then we're going to add this, and it's going to copy all this text, and then we're going to upload it to my email, and then now we'll put that in a flip through. That way I don't have to type all this. It's just all typed in. So, back again. suggested. So C, Control V. Oh my gosh, dude. I remember doing this for the first time a long time ago, and I forgot how many lines I'd have to do this for, because this is insane. We're gonna streamline the process as we go, because I don't have any way I can think to do this right now. But I've got all 28 equations here. I just have to put their coefficients in. Specify remember what happens when this stuff you try to type things and it doesn't let you. Okay, A is going to equal dx divided by dy. B is going to equal dy divided by dx. And then I'll have 2a, I'll have 0.5, I'll have 0.5a, I'll have 200 something lines of code already. This is, how many lines of code is this? Oh my god, it's 800. It's 800. Might not even write 1, 2, and 6 from equation 1. I've got to simplify this. A from equation 2, 1, 2, 3, 7. Oh, I did. Okay, 1 I need, 2 I need, 3 I need, and 7 I need. All the rest of them remain 0. Oh, this looks so much better already. 2, 3, 4, 2, 3, 4, and 8. Makes it so much better. Okay. 4, 5, 9. Extending a pattern. 3, 4, 5, and 9. realizing how many equations that I still have to write, though. This is going to be okay. Equation 10. 5, 9, 10, 13. 5, 9, 10, 13. Alright, we've shrunk this significantly. I mean, a lot. Like, we just do chunks of 3 and 4 and stuff. Some equations have more coefficients than others, but we're gonna be okay now. Yeah. Alright. So 20. 20 is 15, 19, 20, 21, 25. of these coefficients are going to be the same because they're those nodes that we talked about where they're the same color. Those same color nodes are going to have pretty much the same coefficients. If I start noticing that pattern, I'll just put those so we're going to have a few common features, especially in that yellow. Remember where that was, so I'll show you. In here, so we have this big yellow region, like all these equations are going to be the same coefficients. All the orange regions are going to have the same coefficients, all the green. The dark blue will have some of the same. I'll be able to just kind of finagle, but with signs, but they'll be the same idea. This big green bar will have it. These two will have it, but they'll have signs split. These two will have it, but those signs will flip. So stuff like that. Let's continue. So we got had a meltdown there. Okay. 178, I can deal with that. 178 minus this is A and this is B. So when I have node 1, right, like the first element of node 1 is going to be here, and that essentially says negative A is this guy minus 2 times B, right? And then for the next one I just have 2B and then I have A. Okay, so I'm doing that kind of stuff. Here I got B over 2, here I got A, here I got negative A minus B, here's B over 2 again, and I'm just going down the line. And yeah, so a lot of these are going to be pretty similar. A lot of these may even have the exact same purposes. Like if I look and I see like I think 2, 3, and 4 have the same purpose. Like exactly, yeah. They literally have the same thing. So 5 is unique now, so we'll do 5. So 5 is dy y over x, but see, I don't even need to copy paste because of how fast this is. So I'm not even going to worry about it. I am literally just going to keep writing this as this. And then after all of this, we'll say b equals, and then I'll define these node 6, node 7, node 8, 11, 14, 15, 16, that's it, and then we'll divide and we'll get numbers like that for that cube. And then we'll say, hey, what happens if I change K and I get a high? Because right now, that cube, I don't know what K I don't know what my max temperature is. I know it's in your 40s, I don't know if it's in T40s, and I don't know, frankly, if these freaking coefficients are right. As happy as I am to be writing this, it doesn't work. I kind of have to figure out why. Because the report's got to be done, right? And it's not the methods, it's not the results of discussion or even the coding that I really need to get right. It's because he wants us to write it in a form. He wants us to write it in a form where someone who's not taking the class would understand what we're doing. And it's easier to do that with assignment 5, like assignments like assignment 5, which I could pull up that whole statement, but where it's a 1D transient problem in a cylinder. So it's just really easy to just say, here's a node, here's what this is, hey, here's the schematic for this node, this boundary node because this is unique, here's the schematic for this boundary node because it's unique, and then just go along. Here, how many boundary nodes do I have? And how many of them are different? I have to do a schematic for every color on here, and then write a bunch of equations using that schematic. And for the green one, I have to split it all up, so each schematic for that is different. And the 2 red ones are completely different too. Those things. So it's yeah, I think there's only so much I'm gonna do, really. But about this. For 6, it's not going to be that easy. 6 is k times a. 51. 6 is going to be negative k times a times, or negative k times a minus k times 2 times b minus h times dx. Negative k a negative k times 2 times b minus h dx. That's d6, okay? And then this is going to be k times 2b, or 8 times 2 times b, okay? Alright, so I really want to look at mine, because I've memorized the color, see what's going to have the same thing. 6 is neat. 6 is neat. 6 might be related to 14. Yes. This coefficient is the same as 14, 14. And for note 6, k2b, k times 2 times b, the same as 14, 15. And k times a, I'm sure is 14. Oh, it's 14, 19 ka. It's 14, 19. Alright. Alright, cool. So, hey, that's like, actually, these 7, 11, and 15 are the same. They just swap. Their coefficients are not. Just flip. Do a cycle. This is really fast. So, 7, 2. 7, 2 is k times a. Sorry, k times a. Alright, I'm going to save this right now. 7, 6 is k times b divided by 2. 7, 7 is going to be negative k times a minus k times b minus h times dx. 7, 8 is going to be k times b. Alright. Node 7 and node 11 are very similar. So node 7, k dx over 2 k. No, it's not. It's ka over 2. And then it's, yeah, it's different. I'm not gonna write it easy. But okay, so 8. It's actually good verification. Oh no, I just copied and pasted, so it's not. Yeah, it's fine. So, what is it, 1013? Alright. Not stall anymore. 16. K times A. Oh my gosh. I want that to
diagonal, but it's still like, but theoretically from this information you could tell what the shape of this thing is like. You know, you should be able to see like the whole like so from 28 to 14, right? And you can see here like you don't have that much variation because you're dealing with that block. Whereas if you were dealing like, but once you get to node 16, you kind of hit that hole and you see the hole there, and then you get at node 8, and then it dissipates. Oh, there we go. Back to normal. You can see that hole there. I might have saw it. Okay, great. Well, we have our A matrix done. Now let's go B. B. I want to do the same thing in Arduino that I did for A, which is we do this thing again, except I'm not doing the second for loop. It's just going to be B1, B1, 2, B1, 3. The columns, no, sorry, B blank 1, B1, 1, B2, 1, B3, 1, B4, 1. It's going to be a column vector, right? So serial print B, and then I'm going to have B1, comma, no, sorry, B, and then it's going to system out print I, and then it's going to do a comma 1, this equals, and then I'm going to have a space there, and then we're just going to do that, then it should have an LN. Alright, that's good. Let's print that. Everything else is a constant, and it's all the same constant. So it's negative q times dx. So there's that. Wah. All right. 16.1 is probably going to be the same thing. Y, dx, dy over 2, dy, dx over 2. Please be irreversible. Please be reversible. Okay. X equals, this is a huge moment. This is the moment which solidified that, whether this worked or not. I'm going to inverse. Alright. I'm going to divide those matrices. B backslash A. Please die. Please die. Oh, that's not good. Oh, no, we're okay. Those are too big. Which means coefficients are wrong, like a lot. I'm not sure. I'm thinking about what to do. Because I've got to basically restart. Not restart, but I gotta. This process of doing this over could potentially take a long time. I'm glad I got something, but knowing it's that wrong, it's not so. part, like, he did them like I did. Alright, so let's get them out of here. So, for node 1, there's no mirrors. So the whole idea was that there was there's an imaginary number 2 over here. But if you don't do that, which is what I'm seeing in class, you would never do that. If you don't do that, node 2 just conducts to node 1. I'm just treating this as a shape. So if that's the case, this whole 2 minus 1 just goes away. I'm really glad I just multiplied 2 by 2. Everywhere. So that goes away. And then 5. I believe we just take this guy away. Call him 0. And then I'm going to say plus 0. Because there's nothing on the left. Okay, 5. And then pull this out. I don't think, yeah, there's nothing else other than, okay, so then 5 is fixed now. So, we want to prove it. Let's see more color. That's done. Okay. The 24, the last term. No, up. Yeah, the last term on the 24 is. The 28, the second guy that we need there, so it's 0. Node 10, this second guy that we need there. Node 13 didn't need to be there. Gets a 0 as well. Node 18 doesn't need to be there. Gets a 0 as well. Node 23 gets 0. Right. Node 19. The fourth guy there. Six. The bottom guy. No, the last guy that we need there. Let's see, I can't tell. This is exactly what I was talking about. I'm pretty sure that we're using our technique we have to vote. Node 28, he just did 23.7. He did the exact same way that I did. And he did Q's on Apple for one. I mean, it's literally, it's what I have. I'm pretty sure. Let me check it. For node 28, right? For 28. Yeah, it was half of its control volume. I multiplied everything by 2 to keep this. So everything's divided by 2 here, and this is, everything's on top, and everything's divided by 2, because that's there. Bam! Okay. Node 1. Let's rederive some things. Equation for node 1. Alright. So, I think the best way to do this so glad I checked. Whew. I'm telling you, that's the kind of stuff that'll mess you up real bad. Alright, X. And then, X. There we go. Okay, so essentially, we've got bracket here. This guy goes away. And there we go. That is the new node 1 equation. So now that is fixed, I can now use this. I can unhighlight this. Actually, no. I'm going to keep them highlighted. I'm going to highlight them in the middle here because I want to know which ones I need to fix in the code. I want to make sure my code is saved because it'll probably get me out of my MATLAB section. So let's go to my editor here. Let's save. File, save as. Yeah, that's about as simplified as we can get it, right? Excellent. Okay. He's already in 6, isn't he? That's great. Bam. Alright. Name. Move on. 10. Alright, how many did I do? So that took a little bit, but I think it's worth it. Oh, it's absolutely worth it. Like, you know, it's nice that it's not all of them. It's nice that it's not all of them. If it was all of them, I'd probably did this up. So 1, 2, 3, 1, 2, 3, 1, 2. Alright, so I'm about a third of the way done. Okay. That's actually not bad. Alright, so 10. And I don't have to do any like craziness like 6 and 8 and okay, so do 10. That's fine. 10. Now here's 10. Oh, and 10, 13, 18, and 23. These are all going to be the same. Just they're going to be yeah, these are all going to be the same now. So I'm really like more than halfway done. This is great. Alright, sweet. Grade A error arithmetic again. L out of here, L out of here. K. K is gone. Dx. Alright, nice. And 5, 10, 5, 9. Nice. Then 10, and then 13 waits. No 0. Good. All these 10s. No, not you. Thank you. All the 10s. Give them a bracket. And take these 10s away. X over 2y, x over 2y. Looks like I can take that away and do this. And add a plus here, and then we're done. That's it. Alright. Look at my old chart here. that 2 goes away and that 2 goes away. Alright? This goes away. And that goes away. 2, bam, that, alright, good stuff. Especially if I get the right solution, I can write a really, I can write whatever report I want and it'll take it. Cool, so now I only have 1, 2, 3, 4. Oh, wait. Yeah, 1, 2, 3, and 4 equations to do left. 14 sucks. 28's not that bad. 6 sucks where it did it. I should have saw the difference. Oh well. Oh wait. No wait, note 6. It's just that this is in a different place, right? It's the same thing. 6 has negative k dx dy dy dx h. So this 2 goes away. K dy dx is just k dy dx. K dy dx. That 2 doesn't go there. And k dx dy, what happens to that? That just stays. Alright, well it's done. That's it. Boom. And now I have 3 to do. Okay, 19 and 23 are kind of the same. So 19 and 23 are kind of the same. So from above, we have the same, right? Cool. From the right, 23 had a mirror, but from the right, 19 had that. So that 2 just goes away. And then that 2 goes away. And that one stays. Really easy to fix actually. 24 and 28 are really similar to 5. They just have that constant on the right side. So if I go to equation 5, and I'm going to even copy it. If I do this, right? Now look at this real hard. This is this is that, and then this is this thing. It's just that we can't cancel out k's, but it's the same idea. Oh, but I don't like how, okay, I'm gonna do it myself. Yeah, that's, I'm less confident about that. Alright, so 24. I'm gonna do 24 again, so I have to grab it. That's not working. There we go. Okay, so 24. Oh, it's corner notes. It's on the first one.
I'm so glad that that worked, dude. Alright, man. I have code that works. Like, I have code that works.
It took me, what, 5 hours yesterday, plus the, however many hours I'm doing this right now, today, to get these function, because to get them all and then to actually have them work, like, I needed that, man. So I was just trying to accept, like, I know they're gonna be wrong, but they can't be that wrong. But that's on the money for what this should be. And that's what everyone else is talking about. Like, so if we think, let's look at the problem statement here. So compare nodes. There we go. So if I compare nodes here, so this is all the nodal numbers, and these are all their respective like temperatures. Okay. So node 5, let's look at node 5. So node 5, node 6. So node 5 is much hotter than node 6 because node 6 has that convection on it. Node 7, node 8, node 9, node 6, 7, 8, 11, 16, 14. So 14 should be a little more hotter because it's closer to this heat source, right? But 6 should be one of the coldest nodes that it is. It's the coldest node because it's farthest away from the heat source and it's closer to the water. And it's the coldest node. And all of the hottest nodes are going to be 24 through 28, and they're all going to be pretty much the same. The only difference is that 28 is going to be pretty much 28 should be a little hotter than 24. I'm not sure why it's not. You know, because 24 I would think would be getting closer to the water, so 24 should be colder, but 24 is hotter. So the hottest node is node 24. I don't know, I find that strange. But I'm gonna take this and run with it because this is, I don't see any of the nodes being like particularly just weird. Like one of them is 200 or something. 14 and 15 are hotter than 16 and 17. 1, 2, 3, 4, and 5 are the coldest nodes. 1, 2, 3, 4, and 5 are quite cold. The hottest nodes are kind of like here and it just scales up. So, I'm happy with this. I'm going to so now the thing to do. Okay, so there's a couple conclusions I think. I've already done this. What do we have to do now? The thing to do now that I have the solution, is to figure out how I can vary the material type in order to get better cooling. So for example, like I'm putting, let's do this, 100,000 watts per meter squared of heat flux coming in on the bottom there. And 10 to the 5 would be a 1 followed by 5 zeros, right? 10 to the 5 is 100,000. Yes. So this solution's correct. Okay. So, yep. So I did 10 E5, which I think it does 10 times 10 to the 5, which would put another 0 on it. just for curiosity, if I do that, right? If I do this, to get the same answers that I did before, yeah, I get just gigantic answers. So that was the problem. So that should have been 1 E5, not 10 E5. That was my problem. Okay, well, the debugging was successful. We made a good, got a good distribution here. This works. Since this works, what I'm going to try to do is this. I'm going to copy all of this code, Control C, and I'm going to put it in a notepad on my computer. I believe I can copy from them to me. I just can't copy from me to them. Yes, I can. So this is what we're going to do. So I have this on a notepad now, and yep, and yeah. So this will sit on my computer as part of 2 working code. delta y, it hits delta x over 2, travels up. Yes. Conduction from the right, 25, and it travels delta x, it hits delta y over 2. Conduction, heat transfer from the bottom occurs in Q, and it hits delta x over 2, and it hits L. This goes to the other side. The K delta y, I got over 2s everywhere, so I can get rid of those. So there should be a K, there should be a Q delta x, K delta y over delta x, K delta x over delta y. I have probably a KA minus KA
bit ago, but now I'm fairly quite happy. We have a solution that works. I'm about to get. I still need to write the report, and that I just haven't even thought of yet. But I have been nonstop since like 11 o'clock. I kind of want to rush. I kind of don't want to. I'm hyped out now. But there's nothing else for me to really do. I have to start a new thing, and the only new thing I can think of doing is maybe I can just look for a list of materials and try to think of a way that I can present this in a report. So let's see what the prompt statement actually says. It says, although there is interest in operating in higher power levels, system reliability considerations dictate that the maximum cold plate temperature must not exceed 40 degrees Celsius. Using the prescribed cold plate geometry and neural network, assess the effective changes in operating design conditions intended to increase the operating heat flux. So that's what we did. We just said, hey, loop this thing until the maximum temperature reaches 40 and then cause heat flux. We got that. You can consider different materials for the cold plate and or. It says or. It doesn't say and. It says. So we're going to do that. We're going to say consider different materials for the cold plate and or various convective heat transfer coefficients to estimate the upper limit for the heat flux. If I estimate convective heat transfer coefficients, you have to do flow analysis to sort up with whatever fluids you think might work at whatever velocities that you think might work according to what research is done on the thing. You have to do kind of Reynolds number to figure out flow regime. I mean, I'm not doing convective heat transfer. Can you see it? Different materials, I think makes more sense.
T5 of j over here, right? Oh, it's easy. You leave it. But if you want to do it, like you have some problems with explicit methods being stable. If you have T5 of j plus 1 here, you have to actually isolate, take both of these T5 j plus 1s along with coefficients, chuck one to the side, and divide by everything so you can get T5 j plus 1 isolated. And then you can actually start iterating.
Oh, it's on. It's crazy. You have to have your T5J over there as well. On the other side. Your T5J would be considered a constant, I believe. Check what I did here. This is a 1D training problem that I did over here.
You do it kind of the same. Except you have 28. Right, kind of. Ah, here we go. So you can see this was the implicit method, and your T of j is on the right side, and your T of j plus 1 is on this side. So some of your equations I know I've got all of this. I'm just showing my grades. Crazy. On stream, showing my grades. But what are you gonna do, right? Alright, so homework probably more like a 54. I suck at homework. Alright, test 1, 80 or 78. 20%. This is test 2. 83. 20. Project. Probably like on the 85's a really low grade for a project for that project actually. 15. Final grade goal 73. Wait a minute, that's 45 I believe. I think it's oh no, I think it's 35 actually. I think it's 35. I think it's even lower. No, it's gotta be 35. Oh, that's so nice. Oh, dude. Oh, that's so lovely. Oh, dude, what I need. Oh, man. With a curve. 64. You know, that's. I wish it was a little lower, but. What's up? What happened if I get. We were the best project. We were the best one. 60. I mean, you're kidding. And I've got a couple days to study for it. And dang, we're gonna get good. What do I need to get an 80? I'm gonna get 89. Yeah, it's just a B in Alright. Well, you know, I have to take the C plus. The homework killed me. I think if I got a hard grade in the homework, like, oh, dude, yeah, the homework killed me. They did 20 in homework, and you get a grade of 90. Okay. You have to get a 70. Man, what if I just did no homework? I mean, it's still pretty good. But the homework was a lot. I would not want to not do it. So. What? Oh, that's great. If I don't. Still, that's, huh? What happened? I don't know, man. Apparently, I can get if I get a 63, I can get it. 64. Okay. Okay. I'm gonna save everything. Oh, node 24. This is my new node 24 actually. Paste that in. This is my new thing here. Okay. That's node 24. Right? And, yeah. Alright. Good. So, save this again. Close it. Get this PowerPoint. Or this, oh, it's an image. That's even better. Alright, I have to save it. This code. I have saved this code. This works. I know that this works. So, might as well send it to myself again.